Welcome to the deep dive.
Hello again.
Today we are we're undertaking a pretty substantial mission, a highly rewarding one, I think.
Oh, absolutely. This is the good stuff.
We are stripping down the core of modern network architecture, so, going way, way beyond basic routing and switching.
That's right. We've pulled source material that really represents mastery. These are the foundational concepts you need for high-level technical proficiency.
Exactly. And the information here is dense. It's really dense. We're synthesizing knowledge that, in a certification context, you'd need to answer under some pretty serious time pressure. So our mission is to take these 10 critical areas, and we're talking everything from BGP to automation tools, and just pull out the essential nuggets, the what it is, and more importantly, why it matters.
And if we connect this to the bigger picture, this is all about the evolution of the network engineer, isn't it?
Totally.
The old days of manually configuring every single box, well, they're ending. We're moving into a world that's defined by policy, by software modeling, and automation.
Okay, let's unpack this.
Let's do it.
We'll structure this deep dive in, say, 3 parts. First, the architecture distribution and overlays. Then we'll get into optimization and protection. And finally, we'll hit the programmable future.
Sounds like a plan.
So let's dive right in with the wide area network, the WAN.
Perfect place to start.
For a lot of listeners, I think the shift to SD-WAN has been just the biggest change in the last 5 years. It completely replaces that old model of manually configured branch routers.
It really does.
So when we look at, say, the Cisco architecture, what component is the centralized brain, the conductor of the whole orchestra?
That role belongs exclusively to the vSmart controller.
vSmart.
Yep. It is the control plane for the entire architecture. So unlike traditional routing, where every router kind of figures out its own path,
Right.
vSmart is the single source of truth for all the routing information, for the whole topology.
But I mean, every router already manages routing. What's the killer feature that vSmart has that really enables this whole policy-driven idea?
It's the centralized dissemination of IPsec encryption keys.
Ah, okay, the security angle.
Exactly. In a traditional VPN, you have all these decentralized key exchanges. At scale, that's just a management nightmare.
I can only imagine.
But by separating the control plane, the vSmart, from the data plane, which are the routers themselves, vSmart can securely distribute all the keys and enforce policy across thousands of sites almost instantly.
So that separation is the real architectural insight here, isn't it?
It is.
It lets the routers just focus on moving traffic while the control plane, the vSmart, handles all the rules, the policy.
Precisely. It lets you say something high level like traffic from the finance team has to go over our premium link, and vSmart just translates that policy into the actual configuration for every device. That's the power.
Now let's take that same idea, separation, scalability, and move it from the WAN into the data center.
Okay.
For decades, stretching a layer 2 network across a huge data center was a nightmare. You were relying on spanning tree, which we all know the problems there.
Oh, we do. Blocked ports everywhere.
So how does the modern data center solve that? How do you extend layer 2 over a layer 3 network without all that overhead?
The modern solution is VXLAN, Virtual Extensible LAN.
An overlay technology.
Exactly. It's an overlay. And the fundamental mechanism is it's ingeniously simple. You take a normal layer 2 Ethernet frame, and you wrap it up inside a standard layer 3 UDP packet.
So you're basically just tunneling layer 2 traffic over your existing layer 3 network.
That's all it is.
And the physical endpoints that do the wrapping and unwrapping, what are those called?
Those are the VTEPs, the VXLAN tunnel endpoints.
Yeah, that too. So
Typically, you'll find these on the leaf switches in a spine leaf fabric. Sometimes they're even on the host itself. But the VTEP is what does the magic. It does that mapping from layer 2 to layer 3 and back again.
The big payoff here is scalability, right? I mean, traditional VLANs were capped at around 4,000 segments. What does VXLAN give you?
VXLAN gives you a 24-bit identifier, the VNID. That's millions of possible segments. It's a massive leap. But the real insight, the aha moment, is that because you're running this layer 2 overlay over layer 3 underlay,
right,
you can now use layer 3's equal cost multipath routing. ECMP.
Which means you can use all your links at once.
All of them simultaneously. You get massive resilience, huge bandwidth utilization. It's everything that spanning tree literally prevented us from doing.
That discussion on efficiency leads us perfectly into optimization. Even with these modern fabrics, we still deal with legacy protocols.
We do.
And in those old layer 2 domains, you had spanning tree, STP. But if you ran the older PVST plus tree per VLAN spanning tree, the resource hit was just brutal.
Oh, it was exhausting for the switch CPU.
Yeah.
In an enterprise with a few hundred VLANs, PVST Plus meant your switch had to calculate and maintain a totally separate spanning tree instance for every single one.
For every VLAN.
Every single one. That kind of load could bring an older switch to its knees.
So how does multiple spanning tree or MST solve this? How does it improve that efficiency?
The benefit is just consolidation. That's the key word. MST lets you map multiple VLANs to a single spanning tree instance. So instead of running 300 instances, you might run, say, 3 or 4.
Ah, so you group them.
You group them.
Oh.
And that leads to this massive reduction in CPU load, less memory being used, and you get a much more stable and predictable layer 2 world where things convert a lot faster.
Okay, let's pivot a bit. Let's talk about traffic leaving your network. Here's where it gets really interesting. So you're dealing with BGP for global routing. Your company might have, 10 different links to 2 or 3 different providers. How do you decide internally which exit point all your traffic should prefer?
That internal decision is governed by the local preference BGP attribute.
Local preference.
It's one of the highest ranking attributes BGP looks at to pick the best path out of your network, long before it even considers external stuff.
And to be clear, local preference is purely an internal tool, right? The wider internet doesn't see it.
Absolutely correct. It's a non-transitive attribute.
Meaning
it's generated inside your network, your autonomous system, and it only gets passed to your internal BGP peers. You just configure a high local preference value, and higher is better on the link you want everyone to use. It gives you total internal control over your outbound traffic.
So how do engineers manage that across, tens of thousands of routes coming in? You're not setting this manually for every single prefix, are you?
Oh, God, no. That would be insane. No, that's where BGP community strings come in.
Okay.
You don't apply local preference directly to the prefixes. Instead, you tell your border routers to look for specific community tags that your providers apply, and then you use a route map to translate that tag into the local preference value you want.
So you manage policy groups, not individual routes.
Exactly. It makes the whole policy scalable.
That is a massive insight. Okay, let's shift from external routing to internal stability.
Good idea.
Network devices, they're under attack all the time, passive or active. If a device's control plane, its brain gets flooded with junk, it's going to crash. What's the mechanism to prevent that meltdown?
That mechanism is control plane policing, or CoPP.
And what specifically is CoPP trying to protect?
Its primary job is to limit and police the rate of packets that are aimed directly at the device's CPU, its root processor.
So not user traffic.
Not user traffic that's just passing through. This is the traffic the device itself needs to function. Routing protocol updates, SSH, SNMP, ARP, all that critical stuff.
So if I have, say, a denial of service attack targeting my BGP sessions, CoPP is like a shock absorber.
That's a perfect analogy. It uses rate limiters to make sure the CPU never gets overwhelmed. Bad packets get dropped, but the essential services, the routing, the management access, they stay up. The device survives.
Okay, security. It's paramount, and it starts at the edge. Let's talk 802.1x.
Right.
In device connects, you have this three-way handshake. You have the supplicant, the device, and the radius server. What's the third piece in the middle?
The device in the middle, the one acting as the gatekeeper, is the authenticator.
And in the real world, that is?
That's typically the switch or the wireless LAN controller, whatever the endpoint is physically plugging into.
So what's the authenticator's technical job here? Is it just passing messages back and forth?
It's more than that. It manages the physical port state. It relays these EAP messages between the client and the radius server. But critically, it starts with a port blocked. No user traffic gets through.
Until it gets the green light.
Until it gets that access accept message back from radius. Then the authenticator is the one that actually applies the policy and opens up the port. It's the real enforcement point.
Speaking of controllers, let's jump to wireless mobility.
Okay.
In a big campus network, clients are always moving between APs, sometimes crossing over to different controllers. When a client does a layer 3 roam, how does it maintain its session?
The key mechanism during a layer 3 roam is that the client's traffic is tunneled back to the anchor controller.
The anchor controller being the one it first authenticated with.
The very first one.
That's fascinating. But if the client has roamed really far away, doesn't tunneling all that traffic back introduce a lot of latency? That sounds like a trade-off.
It absolutely is a trade-off. You're sacrificing the most optimal path for session persistence. We sometimes call it hairpinning.
But the benefit must be worth it.
Oh, it is. The vital benefit is the client keeps its original IP address.
Ah, so no new DHCP request.
Exactly. No new DHCP. And more importantly, all your established TCP sessions, your video call, your big download, they all stay alive.
Yeah.
For user experience, that seamlessness usually wins.
That makes perfect sense. So we've optimized, we've secured, but how do we prove the network is actually working well? How do we validate performance?
For active validation, you use IP Service Level Agreement, IPSLA.
How is this different from just, say, passively monitoring user traffic with something like NetFlow?
IPSLA is fundamentally active measurement.
What does that mean, active?
It means you instruct your network devices to actually generate synthetic traffic.
Ah, like fake traffic.
Exactly. Like ICMP echo requests or mock VoIP packets, and you send them between 2 points. Because you control the source, the destination, and the time, you get these incredibly precise measurements of latency, jitter, packet loss.
So passive monitoring tells you what happened to user traffic.
Right. IPSLA tells you what will happen to traffic, so you can validate your service quality before users even start complaining.
That's a great distinction. This brings us to the programmable future.
My favorite part.
We've established modern networks are centralized and policy-driven, but none of that works without automation. And for devices to be programmable, they can't just spit out unstructured text anymore.
No. Screen scraping CLI is dead. Or it should be.
There has to be a universal language for describing the data.
And that language is Yang. Yet another next generation.
So Yang isn't a protocol itself. It's more like a blueprint.
That's a great way to put it. It is a structured data modeling language. Its whole job is to define the schema, the layout, the rules, the mandatory fields of all your configuration and state information.
And why is defining that model so crucial for automation?
Because when your automation tool uses a Yang model, it knows exactly what data structure to expect.
No more guesswork.
No more guesswork, no more errors from weird CLI syntax or different OS versions. This structured, predictable data is then exchanged over protocols like Netcon and RESTCon. It's the foundation for reliable infrastructure as code.
Which leads us to the tools that use those models.
Right.
We've got Puppet, Chef, SaltStack, but in networking, one tool seems to dominate, and that's Ansible.
Yes, Ansible. It's really the tool of choice for a lot of network teams.
So what is Ansible's single defining feature that makes it so much easier to deploy on network gear compared to the others?
It is fundamentally agentless.
Agentless.
It doesn't require you to install any client software, any agent on the switches or routers you're managing. Instead, Ansible just uses standard protocols that are already there, mostly SSH.
And why is being agentless such a huge win in a network environment?
Because network devices are, they're purpose-built appliances. They aren't designed to run extra third-party software. That just adds overhead, potential security holes, another thing to troubleshoot.
Right.
By just using SSH, Ansible simplifies everything. You just need credentials and connectivity. You don't have to worry about maintaining client software on hundreds of boxes out in the field.
As networking keeps abstracting away the hardware through software and data models, how long until the only truly custom part of a network deployment is that initial design blueprint, leaving the physical configuration entirely up to an orchestrator?
And if the model becomes the configuration, what's the new bottleneck for performance and scale?
Something to chew on.